So chapter 9, part 1, E1 reactions to form alkenes. Now before we talk much on E1, just like I did in the recorded video, we'll have to explain E2. I'm showing this slide so you can see the different levels on how these yummy grapes are looking. Different color levels, different color grades. So some of them are very black, some are still green, some are reddish, pinkish, different stages of how this thing is ripening. The reason why you're seeing different shades of the colors is because of the number of pi bonds in them. So the biological compound that's giving these colors is getting more pi bonds as you go along towards ripening. So the one that's not ripe does not have much of the pi bonds. It's not very unsaturated. Unsaturation means presence of many pi bonds. So the green one is not very unsaturated, but definitely the black one, this guy right here, it's so dark because it's absorbing much of the UV light, so what's left off for us to see is black or dark purple, whichever way you look at it. So unsaturation is caused by presence of pi bonds, and those pi bonds can be made by E1 or E2, and so we want to see some of the basic reactions, which is E1 and E2, that makes pi bonds in nature and also in the lab. So let's dive in and do some examples. So like I said, I already did the recorded video on the slides. I'm here to work examples, and that's, I think, what you basically need most for now. Alright, so let's compare E1 and E2. Let's start there. Okay, how do I make some line here? So E1 is unimolecular elimination. E2, it's bimolecular elimination. Why bi? Two species determine the rate. So the rate of reaction for E2 is very similar to that of SN2. This time we're gonna call it a substrate, not electrophile, because the rate is affected by the concentration of the substrate and concentration of the base. We are using the base, not the nucleophile. In SN2 we are saying the rate of SN2 rate was equal to the rate constant multiplied by the concentration of the nucleophile and concentration of the electrophile. So in eliminations, we don't use nucleophile, we don't use electrophile, we use substrate and base. So two things determine the rate in E2. In E1, only the substrate, the starting material, will determine the rate. So it's only affected by substrate concentration. So which means if you double the concentration of the base, no effect on rate. Of course, you don't see the concentration of the base, is not part of the equation here. But here, if you double concentration of the base or concentration of this, okay, let's just say concentration of the base for now, because I don't want to get mixed up. I want to be as clear as possible. This is usually very confused, not well conceived by students, so I want to be clear. So if you double the concentration of the base here, the rate of reaction will also have to double because it's part of the rate equation. And if you doubling the concentration of the substrate, and you're gonna be tested on this, by the way. Doubling the concentration of the substrate, rate of reaction will also double. Let's say you double both concentration of the substrate and concentration of the base. The rate increases by a factor of 2 by 2. You just multiply what you're doing. If you're doubling, you multiply by 2 by 2 by 2. If you're tripling, it's 3 by 3. If you triple 1 and double 1, the rate will increase by 3 times 2. So the rate will quadruple. Here, if you double for E1, if you double the concentration of the substrate, that's going to have an effect on the rate. The rate is going to double. Okay? So that's a comparison of E1 and E2. Now, let's go one step further. So I've given you 2 points so far. Point number 3, change the color. Where is my pen? Did someone steal my pen? Alright. So here, reaction follows several steps. Okay, and the rate determining step is formation of carbocation. So again, like SN1, we had to form carbocations. That's why E1 always competes with SN1, because both of them go through formation of carbocation. So we'll say here like in SN1. Here, reaction is concerted like in SN2, no formation of carbocation. Here, let's find another color. So here, this works with weak bases. Example, H2O, CH3OH. Let's just say alcohols. Those are the best examples I can give you. But here, E2 works with strong bases. Example, so we need the conjugate base of water. This will tend to be strong nucleophiles. That's why E2 will compete with SN2. Alkoxides, those are strong bases. Or where R is a carbon containing group. Carbon containing group. Okay, so reaction rate profile. How will the graphs look like? So if you are to plot the graph for E1, because you're forming carbocations versus the graph for E2, which is concerted, this is what you'll at least see. You're gonna see formation of carbocation, then the carbocation is attacked, you get your product. So your reactants will be here, your products will be here. If there's no chemical shift, that is, you'll see only 2 transition states. So your carbocation is gonna be here. I'm gonna just put a plus there. Carbocation will be there as an intermediate. For E2, it's one step, one transition state. Just like so here E1, the energy profile diagram, reaction profile is similar to SN1, formation of carbocation, at least 2 transition state, similar to SN1. That's why they compete. And here for E2, looking at the energy profile diagram, where the x-axis is reaction progress, it's one transition state similar to SN2. So later on, I think in chapter 10, we'll compare all these guys, SN1, E1, E2, SN2. But for now, I just want you to know that there is two elimination reactions, E1 and E2. One is bimolecular, the other one is unimolecular. Okay. All elimination reactions lead to formation of pi bonds. Now, I've scribbled too many things on the board. If you have a question, ask before I do something else.
With the substrate, does that include the leaving group, or is that after the leaving group?
Yeah, the substrate has the leaving group on it.
Okay.
Until the base comes in to take out the leaving group for E2, and for E1, the leaving group just falls off like it fell off in SN1. Good question. Next question. Alright, so now that we know the background, I think it's safe for us to move on and look at the ugly structures that are reacting. So like I said, I'll start with E2. Once you have the basics for E2, I'll now switch on to E1 for the rest of the lecture. Then I think back in chapter 10, we'll still have to come back to E2. Alright, so let's do our E1 mechanism. Remember, elimination gives double bonds, and it's unimolecular. It's unimolecular because of the one, and one thing, the substrate only determines the rate. This is one way of making actually alkenes from alcohols, but we'll discuss much about it soon enough. Oh, I thought I said I want to do E2. Why am I talking about E1? So let me say bimolecular. Please modify. We need to discuss E2 first, because E2 will give us the basis on how double bonds are formed. So let's say E2 bimolecular elimination. So let's give us example of this. Now, what you need to know about elimination reactions, whether E1 or E2, you'll always be removing the beta hydrogens. Remember the hydrogens that we were shifting during hydro shift? That's what we're removing. We're removing beta hydrogens with bases, whether weak or strong, for elimination. But for E2, I'll remind you, it requires strong base. So E2 requires strong base. So let's define those 2 points. So I'm giving you simple structures. So let's say we have that, and then I have this. So you need to tell me. So consider these guys. How many beta hydrogens do we have? You unmute your mic and let's start on molecule number 1. How many beta hydrogens do we have?
6. 1.
Okay, so on this one, I've had 2 answers, 6 and 1. Remember, the carbon bearing the leaving group is the alpha carbon. So then the direct carbons that you have, the immediate neighboring carbons, those are the beta carbons. So you know this has 3 of them, this has 3 of them. So this guy, this molecule number 1, has 6 beta hydrogens. Now that you know, give me the answer for the next one.
3.
3, I agree, 3. Because again, that's alpha. Don't consider these guys. These are alpha hydrogens. The base is not gonna take out the alphas. It's gonna take one of the beta hydrogens. So you have 3. This is very important. If you don't get this, then you are doomed. What about here? How many beta hydrogens?
9.
I agreed. So you have 3 sets of equivalent. So 9 beta hydrogens. Please make sure you understand this, otherwise you'll be so lost. How about this one? How many beta hydrogens?
18.
You are so wrong. 0 beta hydrogens.
Oh.
You're looking at this carbon right there and that carbon right there. Do you have hydrogens there? You don't. The hydrogens are on the gamma carbons, not the beta carbons, because this is your betas. The ones you're counting are on the gamma. How do you even write gamma? They're on the gamma carbons. You have alpha, beta, gamma. So these carbons here on the beta carbons have no hydrogens. You see 4 bonds to the metal, so there's no implied hydrogen. So there's 0 beta hydrogen. Okay, so I think that point is taken in. Now let's give a prototype E2. So I told you E2 requires strong bases, and the strong bases in this example will be OH minus or R minus, where R could be a metal, ethyl ring, or whatever it is. Those and there's one more, NH2 minus. These are the most common for your class. So these fall under the class alkoxides. Like if it's a CH3, it's gonna be called methoxide. Like metal, then methoxide. If it's a ET, ethyl group, it's gonna be ethoxide. But this one right here is the strongest base of these 3. The amide base is the strongest of those 3. It's also used for E2. Now notice that all these guys are negatively charged. So that's one characteristic of a strong base. The guys that are negatively charged and never play a role of a base, the examples are, these are nucleophiles only. I talked about them whenever we are talking about SN2. These guys, though they are negatively charged, they are nucleophiles only. Anything else that's going to be negatively charged will play the role of a base, with the exception of these bullet nucleophiles. So now, let's work examples. So I'll first of all give you the overview of E2. So in fact, I would tell you there's a rule. This rule will be emphasized, I think, in the next class or a class after. There's a rule for E2 that's called anti-periplanar rule, which means the beta hydrogens to be taken out must be opposite in stereochemistry or opposite in configuration. So which means the beta hydrogen must be 180 degrees away from what? Away from the leaving group in orientation. So you really want it to be what you guys call trans. So this is a beta carbon, and I see my hydrogen is down, straight down, Or one would say, if it were a chair, one would say axial down, the BR is straight up. So they are n-type periplanar. We want that. If the hydrogen to be taken out is not in this shape, then it's not going to work with E2. But again, I said we'll discuss much about that later. I just wanted you to know why I'm drawing my beta hydrogen like that. It's because of a rule that follows E2. So I have my OR negative. So we are looking at OR this. This can play the role of a strong base, strong nucleophile. But usually, to avoid SN2, which competes with E2, we usually use protic solvent. That disfavors SN2 from working, because if the solvent here was aprotic, like acetone, then this would play the role of a nucleophile, not the role of a base, and therefore it would attack this carbon, and that leaves, that would be substitution. But we are discussing elimination, so we want to really put factors on the arrow that will help us go E2 elimination. So we usually do heat. Heating must be done for elimination to work, because there's more bond breaking processes than bond forming processes. You need energy. So the base will come and take out the hydrogen. Again, we are using it as a base, not as a nucleophile, because you are thinking elimination. So you take out the n-type periplanar beta hydrogen, and then you use this bond to make a diol bond, and this leaves, because remember we said that E2, like SN2, is concerted. The reaction happens at once, no formation of carbocation. So you take out the beta hydrogen as you lose the leaving group. Guess what you're going to be making? A double bond. So you'll have, so let me show you the hydrogens that are not shown. So at least we're going to be on the same page. So you took out one hydrogen, so you're left with two hydrogens to your left and two hydrogens to your right. Okay. And then there's a double bond. And then, of course, as you did that, your BR fell off. It's a leaving group. But that's not the only product. Your methanol grabbed the hydrogen. So the black hydrogen was taken out by the methanol. I'm a visual student. I'm a visual learner. I think you are also a visual learner, so I'm using color codes as much as I can. So you made a double bond with the red. The methanol accepted the beta hydrogen. So now it's the methoxy, OCH3 minus, methoxy. Or someone would call it methoxide because it's a base. Grabbed the beta hydrogen, and then you use the bond that was bonded to the hydrogen to make a pi bond. So that's the new pi bond. So basically one would just draw this product like that. It's not an equal sign, it's an alkene, ethene actually. That's how you'd make ethene, the babiest alkene possible. And the process is E2. Why? We have a strong base. Protic solvent stops SN2 from working. The reaction is concerted. Okay. Someone has a question?
On the test for the product, will the hydrogens be shown, or will it just be
No,
like
I don't need the
ethene,
hydrogens.
right?
If you draw it this way, I'll be the happiest person on earth.
Alrighty.
And usually we don't need the byproducts unless you are asked for the mechanism, of which I won't ask you for a mechanism because Moodle does not have a tool to draw. Okay, so now let's do more examples now on E2 to make sure we are comfortable, because once you get how E2 works, you'll understand how E1 works. We're kind of doing a back approach. So bear with me with this flipped classroom method. But I think it's working, so it's okay. So let's do number 2. I'm going to draw a structure here of which please draw along with me so you'll follow the process. It's gonna be more hands-on today. Okay, so and my living group is right here. So okay, let me erase that because I'll give you the process thought for that part when time comes. So this one is usually brought as sodium or ET. So one would always neglect the cation and just put a negative charge on the oxygen. That's what you'll have. The ET stands for ethyl, which is this part. So I see it's negatively charged, is part of our general OR group negative. So I definitely know that's a strong base and also happens to be a strong nucleophile. Okay. Now, to make sure that I'm going much of SN2 and much of E2 and less of SN2, I include protic solvent. SN2 will still will work. We'll have the SN2 substitution product as a minor product, but the major is going to be E2 because we used a solvent that kills SN2 process. So I'm thinking E2, so I'm no longer going to think about it as a nucleophile. I'll think of it as a strong base, not as a strong nucleophile. This is a secondary substrate. So remember I told you in fact I should take you back. Let's see. I should take you back here and include one rule that unimolecular prefers tertiary over secondary over primary over methyl X because it forms carbocation. But the problem is that happens to be the same preference for E2. So the only guy that goes opposite to this trend is SN2. So the secondary is right in the middle. In fact, for E2, it does not work with primary because you really have to have 2 carbons for E2 to happen. You have to make a double bond. Same thing applies here. You have to have 2 carbons. So primary and methyl X will not work for E2. So you'll only be going for secondary and tertiary because these guys will only have 1 carbon. You cannot have a double bond between 1 carbon. So primary, let's see. Actually, primary might work, only the methyl X will not work because primary could be 2 carbons or more. So only the methyl X will not work. You cannot have a double bond on 1 carbon that we have on methyl X. So this is out and that's out. So this will be the trend for these two, just similar to SN1, tertiary, secondary, primary. For SN2 is primary is preferred over secondary over tertiary. In fact, it's methyl X preferred over primary over secondary over tertiary for SN2. SN2 is the opposite in the trend. So coming back here, this is a secondary substrate. So this guy can undergo SN1, SN2, E1 or E2. That's why we have to look at what else you are provided on the arrow or added onto that mixture. So I judged is E2 because there's a strong base. So the next thing to do is to do a concerted attack. But before I do that, I have to find my beta hydrogens. I'll ask you again, how many beta hydrogens are present on this molecule? Someone, how many beta hydrogens?
Is it 12?
They are not 12.
They're 3. They're 3?
Yes, they are 3.
Where?
They are 3, but only... Okay, so there are 3 total beta hydrogens, but you have 2 sets. So one is on the left, one set is on the left, and then the other type is on here, and it's pointing away. Okay, so you have these guys right here. I usually show all possible beta hydrogens. Remember, they sit on a neighboring carbon. This is alpha bearing the leaving group. This is beta carbon, so which makes these beta hydrogens.
The other carbons aren't considered beta carbons?
Yeah, because we are calling these beta hydrogens because they are sitting on beta carbons. Just like you take the name of your parent, because you belong to that family. So that's what the baby hydrogen is doing, because carbon, the parent, is beta. This hydrogen must be beta.
So what about the carbon at the bottom, like throughout the whole
This one is
ring?
this one.
Yeah, and the one next
That's
to it.
gamma. This is gamma.
Yeah. Alright.
And then I think this one right here.
So it has to be connected to the leaving group, technically.
The one connected to the leaving group is alpha. Or the one bearing the leaving group is alpha. The carbon connected to the alpha is beta, then the carbon after is gamma. One carbon over is epsilon. We usually don't go that far. Okay. All right. So now that we have an idea on what's going on, let me get rid of this mess. Okay. So now we take out. There's one thing you need to know about the type of products you'll form. So there are stereoisomers that can be made. So now I am trying to explain slide. Which slide is that? The third slide that says stereoselective reaction. So E2 is a stereoselective reaction. You know, there's one way. Either you're going to take out the most substituted beta hydrogen. Of course, that hydrogen must be anti-periplanar. You see, this is a way the leaving group is towards. So it's possible to take this hydrogen out. Whatever happened. Let's see. There we are. It's my stylus misbehaving. So it's possible to take out that hydrogen because you see it's a way the leaving group is towards. So that's 180 degrees apart. So we take out that more substitute hydrogen. We take out the beta hydrogen sitting on a more substituted beta carbon according to a rule we call Zaitsev rule. And I will describe it momentarily. So if you do that reaction, this is the product you get. You get a double bond there. There's your CH3. Notice that the CH3 has lost its weight. Why? Because now this carbon right here is sp2. Trigonal planar. You don't need to show the wedge. Molecular geometry is trigonal planar. So no 3D wedges needed. Okay, so however, I repeat, however, if this base forgets, I'm just going to redraw it for purposes of clarity, but really the same thing happens on the same molecule. However, if the base forgets and finds its way on this other beta hydrogen, okay, because that's also a possibility. This base is not bulky, it's small. So if that happens, then you're going to take out this hydrogen, which is anti-periplanar, and the product that's going to come out is this. Okay, so you're going to make a double bond, and then your method this time keeps its stereochemistry because nothing happened here. So the byproduct here will be what I just showed you. I drew the mechanism down there so that you see how it comes by. So the question is, which of the stereoisomers actually, let's see, these stereoisomers, no, these are regioisomers actually. So the products, there are two products. Either you're making your double bond here or you're making the double bond here. So you see the double bonds are on different regions, so we call these regioisomers. So which is the major? That was my question. The question is, which is major? Can someone tell me?
The first one, because it has more substituents.
Yes, we discussed about this in a previous chapter. I don't know which chapter that was. So here you follow what I called in an earlier chapter, Zaitsev rule. Zaitsev rule states that the more substituted, so it's in reactions where pi bonds are formed, the more substituted alkene product will be the major. Okay, so now let's talk about substitution. I'm going to remind you what we discussed. This one is tetrasubstituted. This is just a review of what you already know. Usually you circle your double bond and ask yourself how many carbons are popping out of the double bond. So that's tetrasubstituted. Obviously this is tri, and then this is di, this is still di, and the Z isomer, this is di-trans, this is di-terminal. The groups are on one end, so it's terminal. This is di-trans, and this is di-cis. And then from there you go to mono substituted, and then from there obviously you go to the babiest, which is unsubstituted, and that happens to be the baby alkene. We call it ethene. So looking at this one right here, I can show my hydrogen and I see that I have 3 carbons bonded directly to the double bond, so this is tri-substituted. This one right here almost looks like this di-cis, but it's a ring, so it's not cis. We don't call it cis. Here it's inside the ring. The ring is rigid. I see 2 carbons bonded directly to it, so this is di-substituted. So definitely this will be the major Zaitsev product based on Zaitsev rule, which happens to be in reactions where pi bonds are formed, the more substituted alkene product will be the major. Someone has a question on that? So remember, the byproduct will always be the alcohol. After the base takes out the beta hydrogen, you'll always get the alcohol version of that base. And of course there's a leaving group which you're not going to be asked to show. So let's do one more example on E2, and then we start E1. Okay, did I lose my pen? I'm gonna ask you to tell me the major to this reaction. Assume E2. In fact, it's not the major, it's going to be the only product. When you're ready, let me know the answer.
The B?
Someone said B. Any other opinion?
A.
Okay. Someone said A. Is there any other opinion? Alright, so the answer is between these two. Let's see what the correct answer is. So, process. Draw out your beta hydrogens. Next, identify that as a strong base because you're assuming E2. This is strong base, strong nucleophile, but because again of the protic solvent, SN2 will fail, where this would have been a nucleophile. So now that we know that, we need to find our anti-periplanar beta hydrogens. Which one is it? Is it going to be hydrogen A, hydrogen B, or hydrogen C? Which hydrogen is anti-periplanar for E2?
B.
Yes, so it's going to be B. So A will never be used. So if you are to take out A and make a double bond, you will have found the answer to be this. So this is not the answer. So we have to take the B right there. Base will take that out. This comes in and that goes out. And that's why I said there's only one product. The metal here was not affected. That's the only product. It happens not to be the Zaitsev product, which would have been A, because again, this one is not anti-periplanar. They are on the same side as the BR. Both of them are towards. They need to be opposite geometry to be 180 degrees apart. So while we would have wanted to take out the A beta hydrogen, it's not on the correct orientation. Here, the beta hydrogen here was on the right orientation. That's why we would have preferred to take it out, because that will give us the Zaitsev product. But here, it's not on the right orientation, so there's no way we should take it out. E2 will not do that. The base will go for the one that's 180 degrees apart. Is that clear? Do you have a question for whoever thought otherwise? Okay. So like I said, E2 will come back for discussion. So let's now flow into E1, where we'll spend the rest of the 20 minutes or so. So now that you understand we are taking out beta hydrogens, I think it's now safe to talk about E1. Unimolecular elimination. So to remind you, you need a weak base So I'm on part 9.3 of your slides that says E1 reaction with alkyl halides. The first slide for E1. So I don't know which slide number that is. Which slide number is this? That's slide 12 of chapter 9, part 1. Reactions with alkyl halides. So E1 reactions with alkyl halides. Okay. Section 9.3. So it's gonna need weak bases. Examples of weak bases obviously are generally you're gonna need anything that has OH to an alcohol. That's a weak base. And then keep in mind there's gonna be formation of carbocation intermediates, but instead of attacking with a nucleophile, we're gonna remove beta hydrogen to form ZF product. So now E1 will never worry. It's gonna always give you ZF product. We don't need the anti-periplanar rule for E1. Remove beta hydrogen to always, no exceptions, always form ZF products. Okay. With new pi bonds, so we are making pi bonds because it's elimination. So here where we are forming carbocation intermediates, you need to expect shifts. You know, shifts could be hydrogen shift, metal shift. Each time you're making carbocation intermediates, expect shifts. So now let's do examples. Let's just quickly dive into examples. So let's say you're given this substrate. It could be a bromine, a chloride, or iodide. And then on here, you are told that you have methanol, for example. I characterize that as a weak base, weak nucleophile. But we are thinking E1. So let's think E1. So the first step is formation of carbocation. In this case, this has to leave before the base removes the beta hydrogen. That's as simple as that. So notice that you have a CH3 there that can give its beta hydrogen. You have a CH3 there. I'm just showing one. Or anyways, the first example. So let me just show all of them so you don't get confused. So you have 9 beta hydrogen, but you have 3 sets of those 9. Only one will be taken out by a base. So you have the set in black, the set in green, the set in red. The equivalents of all those are metal groups. So you can see only the substrate gave you the intermediate carbocation. So this is the rate determining step. That's why E1 is unimolecular. So the first step involves only one molecule, one reactant. So now we have a tertiary carbocation. Usually at this point you want to pause and check and see if shifts will help you. It's already tertiary, no need for shifts. So that's when now your base will come in, your methanol will come in. You have 2 lone pairs on oxygen to make it octet. 2 lone pairs, 2 bonds. So you choose any of these because they are all equivalent, they are all metals. So let me take out one of the black ones. That's why initially I just shown 1 hydrogen, because you only need 1 to do this job. So you take it out and make a double bond. So you're gonna end up with that compound. So here we'll have CH2, and obviously on the other end you have a CH3, and the green hydrogens were not touched, so they are still there. Okay, what happens to the base? the base gained an extra hydrogen. The weak base methanol gained an extra hydrogen, so it's going to be CH3 or CH2, OH2. This is a byproduct. Usually we don't ask about it in the test. All that you need to show in the test is this guy. Keep in mind, you would have taken out one of the reds, you would have taken out one of the greens. You will always get the same product we call isoprene unit. So that's the baby simplest E1 possible. Okay. Someone has a question before I do the second example on the process of E1?
So you just said that no matter which beta hydrogen we take out, it's going to give you the same product?
Yeah, so for example, if you take out the CH3 in red, then this is what you're going to get. Let me show you.
Right.
So we don't have to worry
about like regioisomers.
Yeah, there's no regioisomers because this is the same molecule just rotated.
Okay.
Similarly, taking out one of the green hydrogens, you're going to get a molecule like this. It's just the same molecule rotated on the plane. So there's no regioisomers there. For this example, there's no regioisomers. Sometimes you get regioisomers, sometimes you don't. Depends on what you're asked. So now let's see, what about this substrate? Assuming we are going E1 this time, our weak base is going to be water. So we assume E1. Our assumption is E1. So again, the base does not take part in the first step. We really have to form the carbocation before we do anything. There's a plus sign on there. So this is secondary. Okay. We expect shifts. Obviously shift is possible because this carbon right here is a tertiary carbon. This is a primary carbon. Like we said about shifts, you shift from a neighboring beta carbon of higher degree, which would be this. The hydrogen is not shown. That's what we need to move. So we'll do our shift right there. So by H shift, moving the hydrogen, you're gonna get the hydrogen comes here. Really, there's a hydrogen here that's not shown. You know, carbocations always have 3 bonds. The C plus always has 3 bonds. There's a hydrogen there. Now you have 2 of them after the shift. So pretend this is what you moved. Then that's what you moved. So now there are 2 of them. The bond is lost. This carbon is 1 bond less. It gets a plus for more charge. The other way to look at it, carbon has a valency of 4. This guy has has 3 valent electrons. You need to add 1 to make it 4. So we put a plus charge. So now it's a tertiary because now the C plus is bonded to 3 other carbons. And that's the only time the base comes in. If this was SN1, the water will simply attack the C plus. But we are thinking E1. So the water is used as a base, not as a nucleophile. So let's take out one of these. No need to worry about anti-periplanar rule. So Moses, what did you do? Are you sleeping? You need to choose black, not white. How can you use white on a whiteboard? Okay, so you get a double bond. Notice that you have other beta hydrogens, but I chose to take out the one that's sitting on a most saturated carbon because I said you should always, for E1, always, no matter what, always remove beta hydrogens that are available to form the ZZ product, unless the beta hydrogens are not there. So prioritize the hydrogens which are sitting on a more saturated beta carbon. Always try to make the ZZ product for E1. unless the beta hydrogens are non-existent. Okay, so the water that picked up the hydrogen becomes H3O plus because H2O gained a hydrogen, now it's H3O. The oxygen used its lone pair, so it has to bear a plus sign on the byproduct. Again, this is what will be my interest. Do you have a question at that point? Are we good, or is it too much chemistry?
It's always too much chemistry, but we're good.
No, oh no, oh no. Bear with me, bear with me, bear with me, bear with me. I'm trying to make things work, and you know that.
So you picked that hydrogen that's circled rather than the two hydrogens in red.
Yes. Because
so that it would be tri.
Yeah, because I get this as tri-substituted. If the base chose to take out this hydrogen, for example, then you're gonna make a double bond here, and your product will look like this. That's di-substituted.
Yeah.
And the rule for E2 is to go for the most Z-safe product, the best Z-safe product. Are we good with that?
Yes.
Yes.
Okay. So I'm gonna do two more examples and stop there. For the next class, it's gonna be recorded live during class because of the many graphs that are coming up. So I can't go past the slide we are currently on. That one will be just instant recording because of the many graphs that are on there. Now let me do more examples for E1. Oh, not really E1. I'm gonna try to summarize today's lecture with a few more examples, so to speak. Okay, so Moses, what do you want to do? Okay, let's go back here. So I'm giving you H2O. Think E1, think E2. Which process is likely to go here? E1 or E2?
E1.
E1.
What's your reasoning?
Because it's H2O is the base.
Is it a strong or a weak base?
It's a weak base.
So that's how you think. Weak base. E2 would have wanted a strong base. Now if it's E1, now you know that this thing will fall off. So now you can proceed with your mechanism on your scratch paper. So you get a secondary. We have a chance to rearrange. So that's what the molecule do, going for the major product. So now this is a carbocation. The wedge is lost because this carbon right here is sp2. It must be planar. It's not out of plane. Here you really had a hydrogen. So now there are two after the shift. So that's where now the water will come to take out the beta hydrogen. You either have that or one of that or one of these ones here. So one would either take out A or B and not C, because A and B are equivalent. Both of them are CH2s. The molecule is symmetrical. You can take out either or. So the product should come from obstruction of one of those hydrogens. I'm gonna just choose the one that's below for purposes of the mechanism. So let's see, the product will make. I have to erase this black arrow. So after making the carbocation, you take out that, make a double bond, and you are making the carbocation because it's a process of E1. So I'm not gonna take out the C beta hydrogen because it's sitting on a less substituted carbon. So the product must be like that. Notice that if you take out the one that's on top, the hydrogen B, you get the product like this. These two guys are the same, it's just the molecule pancake flipped. So you just draw one of these. Okay.
So the beta hydrogen you're taking is just not off of the substituent of the ring, because that would make it
if you take out this hydrogen using the base, you're gonna get this product. This is di-substituted. The double bond is bonded to two carbons, but these two guys are the same. They are tri-substituted. I see that carbon, and that carbon. This is tri-substituted. This is a product. That's the reasoning. Okay, so now let's do this one. Which profile will go, E1 or E2 for this one?
E2.
E2, correct. The reason is the methoxide is a strong base. Strong bases work with E2. Okay, so we come here and look for the beta hydrogens. Right now here there's no beta hydrogen. But on here, on this beta carbon, you at least have one that is anti. One is away. One hydrogen is always away. One hydrogen is always towards. The base will take out one that's preferable, which is anti-periplanar, which is this one, which is towards because the leaving group is away. We don't take out the one that's away. We take this one that's towards because the leaving group is away, following anti-periplanar rule. Alright, so let's see how we're gonna do. We get a double bond. Okay, so that will be a product. Obviously, byproducts will be the red hydrogen taken out by the strong base in black. And then obviously you have sodium and chlorine. That will give you sodium chloride. Usually you just ignore the cation and just put a negative on the neighboring electronegative element. So let's stop there for today, unless you have a question.